So in the data analytic or data science lifecycle, let's say you've already chosen your data set, and then the next step, you've already performed data pre-processing, such as data cleaning, where you handle missing values, you've removed the noise and outliers, perform data transformation, and so on and so forth. So the next step, you've already identified, selected, or created your model. In our case here, for a classification problem, for example, here, logistic regression. Okay, so let's say we've selected logistic regression. Now, the next step is to work on model evaluation. So what is model evaluation? Now, this is a process of assessing the performance of a machine learning model with the aim of determining the quality and the usefulness for a particular task. Now, we carry out this task so that we can compare models prediction to the actual outcome on a data set, especially that which the model has not seen before. So we use model evaluation to make comparison using various metrics. So for example, here we use the following metrics for classification. So in our case here, because this is a classification task, we can use precision, recall, F1 score, ROC or AUC, precision, recall, curve, and so on and so forth. For regression, we're going to look at this in a separate video, but we talk about MAE, RMSE, root mean squared, error, and so on and so forth. All right, so again here, all this would depend on the problem type. Okay, now let's look at an example here. Suppose we have a data set which has maybe 1,000 samples, right? So let's say we have 1,000 samples here for a binary classification task. Okay, so the goal here is to predict whether a given sample belongs to a class. So this class could be either we have a yes or no. So let's say this is a binary classification task, has two possible outcomes, Y or no, right? So, and then we train our model on, we train using two models, let's say model A and model B, right? So we've trained this on our training data set. Then we, for example, we use a test set, for example. And this test set, let's say, has 100 samples, right? So the first thing we want to do is to evaluate this model on this test set. Then we use this classification or other metrics, classification metrics like accuracy, precision, recall, F1 score, and then we record the the results here for model A, right? So let's say result A. We do the same here again. We do also record the accuracy, precision, recall, F1 score, and we record the results for model B. So in our case here will be model B. So based on these results, we want to select the best model, right? So out of these two, which model performs the best, right? So we may choose to train another model, or we can, again here, do some fine tuning. So we can either fine tune here to improve the performance of our model, or probably just, on the existing model, maybe A or B, or probably just go for another model, right? So this is the goal here for our model evaluation. Again, so we're going to look at how individually look at the metrics for performance, classification performance. How do we evaluate the performance of a model, right? Our emphasis here is on predictive capability of a model, right? And to do this, we're going to use something called confusion matrix, right? A confusion matrix essentially is just a table, or in our case here, it's just a performance measures technique for machine learning classification, right? All right, but before we do that, let's look at why we perform model evaluation. So the first reason here is model selection. Now, model evaluation is used to compare the performance of different models, right? And to select the best one. We've already looked at this in the previous slide. So this is especially important, especially where you have multiple models, in our case here, model A and model B to choose from. and when building a new model from scratch. Okay, the next reason here is hyperparameter tuning. Again, here, model evaluation is used to fine-tune hyperparameters of a model. These hyperparameters, could be, for example, the learning rate, regularization strength. If you are using random forest, you can also fine-tune by, changing the number of trees in a random forest, and so on and so forth. Okay. Again, so we adjust these hyperparameters of a model, right? So the optimal hyperparameters depends on the specific problem, okay? The size and structure of the training data. And we tune that to the desired performance. Again, it's important to note that you can actually significantly improve the model's performance and also improve its generalization ability by just performing a bit of fine-tuning on that model. Okay, another case in point here is overfitting and underfitting detection. Now, model evaluation will help you to detect some of these anomalies, right? Which occur when a model is too complex in the case of overfitting, or it's very simplistic in the case of underfitting. Of course, here overfitting simply just means the model fits the training data too closely and does not generalize well to new data, okay? While underfitting here essentially just means it's too simple and does not capture the underlying relationship in your data set. So model evaluation will help you, or will help us find the optimal balance between overfitting and underfitting, okay? So sometimes we also talk about the bias variance trade-off, okay? And then here, performance assessment is another reason. Model evaluation provides an assessment of the model's performance on a given task. Now, the information we get here will help us determine if the model is suitable for deployment or we need to further improve as and when it's necessary. And then lastly here, we also use model evaluation for error analysis, right? So we can use to identify sources of errors in our model's prediction. So again, we can use this information to improve the model, or we can actually add more data, right, in our model to better address the problem. Now let's look at the confusion matrix, right? So at the onset, we said confusion matrix is just a table summary of the total correct and incorrect prediction made by a classifier. So as you can see here, we have this table. Now, we use this table to measure the performance of a classification model. Okay, in another video, look at how to measure the performance of a regression model. Okay, now to evaluate the performance of a classification model, we compute several performance metrics such as accuracy, precision, recall, and F1 score. We're going to look at this in the next video. But again, here at the top here, we have the true class, sometimes called this the ground truth labels, positive and negative. Here we have predicted class, positive, negative. And then here we have, true positive. In fact, let's go to the next slide just to look at some of this. So from that table, we can see that we have true positive. Now, true positive here essentially just means we predicted positive, right? And actually, it's actually, the actual value is positive, meaning it's true. So that's what true positive means, an outcome where the model correctly predicts the positive. Another metric here is true negative, right? Here means we predicted negative and actually it is true, or the value is actually negative. So that's how to look at this. Essentially here, the outcome where the model correctly predicts the negative. Then false negative, we predicted that it's actually positive, but it is actually false, okay? So the outcome where the model incorrectly predicts the positive class. Then lastly here, false negative just means that we predicted negative and it's actually false, okay? Now this outcome is where the model incorrectly predicts the negative class, all right? So these values can help us identify the strength and weakness of a classifier, all right? And based on that, you can make informed decisions whether to fine-tune and improve the performance or go back to your data set and try to perform a little bit of more data preprocessing. Now, another thing I just want to mention here is that a high number of false negative here, a high number of false negative, indicates that classifier is not identify certain classes very well. Okay, and then here a high number of false positive here may indicate that it's generating too many false alarms, right? So in summary, we can say that this confusion matrix, right? In summary, the confusion matrix just is a valuable tool for evaluating and interpreting the performance of machine learning algorithms. Now, let's look at some of these metrics that we can compute from our confusion matrix. The first metric is called the accuracy. Now, this accuracy essentially is just a computation of some of the metrics we've already looked at, right? The true positive, so it's given by true positive plus true negative, right? Divided by true positive plus true negative plus false positive plus false negative. Okay. Now, this accuracy just measures the proportion of correct prediction made by the model. If you look at it closely, you'll see it's just the proportion of the correct prediction. True positive, all the classes here are true positive. True negative, all the classes here are true negative. Divided by, okay, we divide this by the total number of predictions. So all this is the total number of prediction, the total in this quadrant or in this confusion matrix. Again, here we have precision. Okay. Another thing I just want to mention here, one of the limitations of accuracy here is that, again, it's not suited for imbalanced data sets. So if you have two classes here, so let's say this is class A, right? And then this is class B. Okay, so this is an imbalanced data set. So again, here the accuracy might not be well suited for this. So you want a binary classification, you want something that at least is almost balanced, right? The classes are actually balanced, right? Okay. Again, also it's we can say also it's not suited for a skewed data set. Now let's move on to precision. So precision here essentially just is given by this equation: true positive divided by true positive plus false positive. In other words, it tells us how many predictions are actually positive, right? Out of all the total positive predicted. So the false positive here essentially just means we predicted positive, okay, and it's actually false, right? Essentially here we just want to include everything that was predicted as positive. So it measures the proportion of positive predictions that are actually correct, okay? And then we have recall here. Sometimes we refer to this as sensitivity, okay? It's given by TP, true positive, divided by true positive plus false negative. Now, this just measures how many observations of the positive class, right, are actually predicted as positive. Okay, this is actually a good metric when we want to capture as many positive as possible, right? So again, these are very important measures. And then we have F1 score. Sometimes we call this harmonic mean. It's just the it's given by this equation, to multiply by the precision times recall divided by precision plus recall. Again, here a high value of F1 score ensures that both precision and recall are reasonably high. Okay. And then lastly, we have specificity, which is just given by this equation: true negative divided by true negative plus false positive. Okay. So this is a metric we use in binary classification to measure the proportion of negative instances that are correctly predicted as negative. So here, basically, just look at the strength of the negative class, how much of the negative class were predicted. Now, I just want to quickly give an example here. So when we look at recall here, right? Suppose here we want to predict a model that, whether a model to predict whether a patient, in our case here, whether a patient has cancer or not. Okay, a high recall score here indicates the model is able to identify most of the positive cases, meaning that patients who have a cancer. Okay, and this is very true because this is very important in the medical domain, right? In the medical domain, recall is very important because we don't want to send a patient who is actually sick home and we misdiagnose that. We want to capture as much as possible those who need treatment strategies or treatment attention. because this can have very serious or catastrophic consequences. In contrast, when we talk about precision here, again, we can see here, a high precision does not guarantee. A high precision here does not guarantee that all positive cases are detected. Now, so in these two cases, you can see recall here will be the preferred evaluation metrics, especially in the medical domain, okay, because it gives a better indication of this model's ability, right, to identify all instances, in our case here, whether a patient has cancer or not, and we don't want to miss any positive cases. So here we want this FN, the false negative, to be low as possible, right? Okay. So again, that's just that. And then of course, other metrics, we have TPR, which is just sensitivity. It's called the true positive rate. Probability that positive prediction will be true. We have TNR, we have FNR, false negative rate, FPR, false positive rate, is given by this equation, FDR, false discovery rate, and we have MCC, Matthews correlation coefficient. Okay. All right, and then we just want to look at one example here. So suppose we have a data set, right, of 500 patients, and let's say we choose a random forest classifier, okay? This is a classification algorithm to predict whether a patient has cancer or not, okay? So let's say true positive is 250, false positive is 40, true negative is 200, and false negative is 10. So let's compute. So let's go ahead and compute. So we are saying here, true negative actually is 200. So we have 200 here, right? And then false negative, we have 10. So let me just write this correctly here. We have 200. False positive, we have 40. All right. And then true positive, we have 250. Okay. So our first metric we want to compute is accuracy. Okay. So accuracy is given by this formula or equation: true positive plus true negative divided by true positive plus true negative plus false negative and false positive. So we just plug in the numbers and we get that is 0.9, essentially 90%. Again, for precision, we plug in the numbers in this equation and we get 0.86. Essentially, this is the same thing as saying model performs at 86%, right? Again, if we perform recall here, so let's go and look at recall here. You can see we plug in the numbers and we get 96%. So in this illustration, we can see that precision here is just essentially the true positive divided by both the positive, even if they were false, and the true positive. Recall here, we want to get as many relevant items that were correctly identified as positive. See, the true positive out of all the false negative, which of course are actually positive. Okay, so that's recall. And then lastly here, if you plug in the numbers for false F1 score, again, it gives you 91%. Now, from this, you can already see that the accuracy is 90%, recall is 96%, precision is 86%, and F1 score is 91%, all right? So here we can observe that recall is the highest, followed by F1 score, right? Accuracy and precision. Now, in a medical diagnosis, in our case here, we want to predict whether a patient has cancer or not, right? Recall is usually more important as this false negative. So we want to reduce this false negative. You can see if the false negative goes up, then the recall, the false negative here goes up, then the recall here will go down, right? So again, here it's more important as false negatives can lead to missed diagnosis. We don't want that, right? And this can lead to very catastrophic consequences, okay? So in this example, we can already conclude that recall is very important because our task here is to capture as many, correctly predict as many patients who have cancer, okay, the positive class. All right, and that's how to, evaluate the performance of a classification model using accuracy, precision, recall, and F1 score. In another video, we'll look at how, to use other measures to actually improve the performance of a classification model.